everything we're learning. Sort of an issue. Let's move on to simple regression. We won't catch up completely today, but we're making progress. We're closing the gap. Now, the regression, so kind of transitioning now into regression. So we've talked about correlation. So one thing we can think about with R, the correlation, and even when we get into regression, we're going to talk about R squared. Correlation, R, is really a descriptive measure. It describes, kind of the shape of that potato, which directions it headed, how is it like a big round potato, or is it like a thin hot dog sort of shape? That's
fingerling, if you will.
A what?
A fingerling potato.
Oh, there you go. I need to get pictures of potatoes. We could have pick a potato and I match the potato with the correlation coefficient. I need to get some sleep. So we use correlation kind of to describe that relation. But where we'll use the concept a lot is R squared, when you square the correlation coefficient. And what the R squared represents, which we'll get to in just a minute, we're going to actually use all semester long. And that's this idea that the R squared is the proportion of the variance in Y, in our outcome, that's related to or accounted for by its relationship with X. If you square the correlation coefficient, it gives you an indicator of the proportion of the variance in Y that's related to or accounted for by X. So kind of to see what I mean by that, let's think about, let's look at this. I want to look at the relationship between parent reading ability and the child reading. How much the parent reads to the child and child's reading ability, right? So if I know nothing, Sergeant Schultz, I know nothing. Hogan's Heroes, I know nothing. And I'm trying to guess some child's reading ability. I'm going to guess, well, they're probably somewhere in the middle. I don't know anything about them. They're probably somewhere in the middle, but it could be anywhere in this range, right? They could be way down here, they could be way up there, they could be anywhere in that range. On the other hand, if I know that there's a strong association between parent reading ability and how much the parent reads to the child and the child's reading ability, I know there's a strong correlation. And I say, now you no longer start Sergeant Schultz. Now I'm going to tell you something. I'm going to tell you that parent reads to their child every night for half an hour. Going to bed. The little 4-year-old kid. They're reading to them constantly. Then you're thinking, okay, now I know something. I'm thinking they're going to read. Yeah, the child's reading ability is probably pretty good if the parent's putting that much time in with them. And the variability, I'm not guessing anywhere in this range anymore. I think, it's much smaller. They're somewhere in a much tighter range. I'm not left blindly guessing anywhere in this range. I've whittled it down to, they're somewhere in this range. That's the idea, kind of, with R squared. Now, of course, notice R squared, we're talking variance, which is squared, and these aren't squared values. But conceptually, I think that's a nice way to think about it. That the R squared tells us, when I don't know anything, I'm making guesses anywhere in this range. Now, as my R squared gets bigger, I'm still guessing. I don't know exactly what the number is, but I'm able to more precisely estimate what the value is. And how much that's reduced in squared terms is equal to your R squared. Pretty cool. Now notice, it doesn't mean that we're right. Some of the answers I've seen over the years with some questions, and I'm giving you, this may not be on any of the assignments. but some of the answers people would give, like, oh, what does r squared? They'd talk about, oh, if the r squared's 0.5, it means your predicted score is right 50% of the time. No, it doesn't. It's like your predicted score is probably never exactly right. It's always a little bit off. Or half of the time, half of the regression line goes through half of the points. No. It's r squared is telling you just how much more precise you're able to make a prediction. That's what it's. But that's powerful. If you're trying to guess, is how well a child's going to do in college, and you're thinking, oh, I have no idea. But if I know kind of this and this and this and this about them, I'm able to narrow it down. That's helpful information. If I'm anyway, so that's kind of behind r squared. It's if the r squared is 0.5, it just tells us 50% of the variance in reading scores is related to their parents, how much their parent reads to them. I've already kind of talked about all this. I kind of got ahead of myself. So r squared is that proportion of the variance that how much we started with this much unknown, this much variability that we're trying to explain. R squared tells us how much of that we now understand. And 1 minus r squared is how much is still left unexplained. Right? So r squared is the proportion. You can think of they add up to 100%. This is the proportion that we understand. 1 minus r squared is the proportion that's still unexplained, that's still left for us to try to uncover or discover. Let's keep going. Now, to do regression, so let's look at kind of how do we do simple regression first. We'll start with one. And when I say simple, people use the term simple regression. Just means there's only one independent variable. There's one predictor that you're doing. So starting with simple regression, there has to be some relationship between x and y. Whatever the two variables are, there has to be some relationship. If you're trying to do a regression of shoe size and SAT scores, it's not going to work. There needs to be some relationship between the two. Higher SAT scores, better college grades, more reading by the parent, higher child reading scores. Kids who study more do higher in high school math, whatever. What we're going to calculate and what we're going to focus on for our course is what's called least squares regression. And typically there's other types of regression, but when people talk about regression and multiple regression, they're almost always talking about what's called least squares regression. And we'll see, you can probably guess kind of where that might be coming from in terms of think of the sum of squares and characteristics of the sum of squares. But the least squares regression line is a line that will pass through the data, and it tells us what our prediction would be for a child, for someone's score. It tells us what we would predict for some y based on a score of x. And if you think back to high school geometry, a regression, what's the formula for a line is y is, your y is equal to some, well, there's all sorts of ways it might have been presented. mx, the slope, times your x plus b, or the regression coefficient times x plus a. It's some intercept value plus the slope times whatever your value. You just plug in values. Well, we'll get into that. The least squares regression line, we just plug in the values based on an x, and it gives you a predicted y. And again, you might have seen any of these sorts of notations. They're all exactly the same. It's just different ways of saying the same thing. We're going to use this last one and the one up there, b0 plus b1 times x, because that just translates easier for multiple regression, which we'll be getting into shortly. But undergrad textbooks will often use mx plus b or mx plus a. So let's think back. I've just kind of said that. This formula, B0 plus B1 times X, will generate a nice straight line. Kind of, I've got it here. You plug in a value for X, and it'll give you a predicted value for Y. So one part of this equation, we're going to see the B0 is what's called the y-intercept. And by y-intercept, we just mean it's the predicted value when X is equal to 0. It's your predicted value for Y when X is equal to 0. And you can see, well, that's kind of obvious, because if X is equal to 0, you just plug in 0. B1 times X, B1 times 0 drops out, and your predicted Y is B0. And you might ask, why would we have it something called B0 and B1? Why wouldn't we make this B1 and B2? Why would we number these weights? Why would we use 0? Well, we're going to see later, because notice I've got one X, and this B1 is with the first X. And B2 will be with the second X, and B3 will be with the third X, and 4. There's no X with this one, so it's with the 0th X. Just kind of geek way of time. Otherwise, it'd be a little confusing if my second X has a third, if the third regression coefficient is with the second X. It's an easy way to start to mix things up. So it's just a numbering scheme. So these are values. So B0 could be 3, it could be 10, it's some number that's part of our regression equation. And it's the predicted score of Y when X is equal to 0. So if I study 0 hours a week, what's my predicted GPA? 1.3. So B0 would be 1.3. If it's my, the slope, B1 is what's called the slope. And you can think of that as the increase in Y with a unit increase in X. So if X increases 1, whatever it is, 1 hour of studying, $1,000 of income, whatever. If X increases 1, Y goes up or down exactly equal to B1. So if every hour I study, my grades go up 0.2, B1 would be 0.2. And you can kind of see mathematically why that works, because right, if I plug in B0 plus B1 times X plus 1, so I've studied 1 extra hour, that just solves to B1 times X plus B1. That 1 hour, right, is 1 additional B1 on my X. Another way people talk about it is rise over run. You go up and over, right? So if I'm going up 0.2 for every 1 hour of studying. Now our predictions, so we have the regression equation. As you can see, the scores don't exactly fall on the line, right? In fact, it's probably unlikely that many scores will fall exactly on the line. They're going to be above some are above, some are below, right? They're kind of all scattered around. The difference between what's observed and what's predicted is called a residual. Now, you also see people talk about these as errors. Residuals, exactly the same. Just some people prefer different terms. Mathematically, you can think about the residual is Y sub I, my observed score, minus the Y hat is a way of saying our predicted score. So you see the Y with a little check, it's called Y hat. Is I'm trying to think of, how would you describe that?
Like a little carrot.
A little carrot.
I like the hat.
But it's not called Y carrot, it's called Y hat.
It's like the hat of a beret.
There was a stat professor when I was in school whose email account was Y hatted. That was cool. He must have been so fast when they opened up the email system to claim that as a, anyway. At one point, I think I was looking for driver for license plates. That would be y hat, but it was gone. Anyway, where were we going to go? Oh, so that's just my real score minus my predicted score. That's what a residual is. So if my score is higher than you predicted, oh look, my grades, you predicted I'd have a 3.2 given how much I studied, but I got a 3.4. 3.4 minus 3.2, my residual is 0.2. I'm 0.2 higher than you predicted. If, on the other hand, you predicted I'd have a GPA of 3.6, and my GPA, my real GPA is 3. 3 minus 3.6 is negative 0.6. My residual is negative, meaning I'm below the predicted score. So positive residuals mean you're above your predicted score. Negative residuals mean you're below the predicted score. Other ways you may see exactly the same thing written is yi, right? Y sub I. I is just means it's person i's score on y, minus y prime. And it's got the little prime symbol next to it. I. Y prime is just another way of saying y hat. It's just another notation for predicted scores. Okay? The characteristics of the residuals. The sum of the residuals is going to be equal to 0 with least squares regression. So there'll be some residuals below, some scores will be below the line, some scores will be above the line, but on average, if you add up everybody's residual, right, my observed minus my predicted, y caret.
It equals 0 in an infinite sample or in every sample?
And it'll equal 0. That's just yes. So the sum of the residuals is going to be 0. That's a characteristic. Well, in reality, that's a characteristic of the mean. So that's kind of if you think of just predicting the mean, you know you're going to get those equal to 0. What's cool about the least squares regression line and where it gets its name is that if you square those residuals, the sum of the squared residuals for least squares regression will be a minimum. So right, we know, I mean, in this sense, because this doesn't define and it doesn't define one line. You can't say, well, I'll come up with a line that this is I digress. But you could think if we just look at the sum of the residuals being 0, I could have this line would give me, look, they kind of cancel out. But I could also just pick a straight flat line right equal to the mean. And we know I'll have big residuals, some really big residuals, negative residuals, and some really big positive residuals if I had just a straight line right across the middle. But they'd still sum to 0 because we know that the sum of scores around the mean is always equal to 0. So this doesn't help us form the line. But the fact that the least squares regression, that the sum of the squared residuals is a minimum, that's what tells us, that's what shapes the regression line. It's the one line that goes through the data where the sum of the squared residuals is a minimum. If you made the line a little higher, the residuals are going to be bigger. You make the line a little more flat, the residuals will be a little bigger. Least squares regression gives you the intercept and slope that gives you the very smallest sum of squared residuals. That's why it's called least squares regression. Pretty cool. Any other line will give you larger numbers. And let us stop right there. Next